Hi there, and welcome to Chapter 4.2 from Stevens' Matrices, Vectors, and 3D Math. In this chapter, we're going to talk about partial derivatives, gradients, and normal vectors. Before I get into that, I'm going to switch this over to full screen mode. There we go. Okay, so here's the situation. Whenever you were dealing with the function of one variable, and we said something like y equals f of x, we had the derivative that we called y primed. We called it df dx. We called it f primed of x. We had all sorts of names for it. Now the problem is that when we have z equals f of xy, we have two independent variables, x and y, and so we will have partial derivatives. One derivative with respect to the first variable, and another derivative with respect to the second variable. And these have formal definitions that in the end turn out to just some basic simple rules, but the definitions are identical to what you may recall from one-dimensional calculus. In one-dimensional calculus, there was no y part here, right? And if you get rid of your y part here, here, and here, it's the identical definition of the derivative of f with respect to x. But now, since I have two variables, this is called the partial derivative of f with respect to x. It's denoted with this partial, it's not the same d, df dx, right? The partial derivative symbol. And that's also sometimes denoted f sub x. Notice f primed, that's gone. Because there's more than one independent variable, we don't know what derivative you're taking. So you have to denote what's the independent variable that you're differentiating with respect to, and you denote that either here or here. And then the formal definition is just if you take a small step in the x direction, the positive x direction, subtract from the function evaluated where you originally were divided by the size of that step. When you let that step size go to 0, you get this partial derivative. It is the derivative in the positive x direction. Likewise, if you play the same game, only you're taking the derivative with respect to y, you get the partial derivative of f with respect to y. Denoted the same way, only we have a y where an x was, and now we're taking a little step in the y direction. Right? And we're letting that step size go to 0, and in the limit, that gives us our definition of the derivative. Now the nice thing is, if you can just pretend that one variable is a constant while considering the other variable the actual independent variable, partial differentiation, the practice is really quite simple. I'll show you what I mean. Suppose I have my function from the paraboloid. F of x, y is x squared plus y squared plus 2. If I want the partial with respect to x, all I do is, there's my only x, so the derivative of that with respect to x is 2x. This is a constant as far as x is concerned. So a constant, when you differentiate that, goes to 0. This is always a constant, so all you get is 2x. And likewise, f sub y, the partial of f with respect to y, well, that's a constant, so it goes away. That's a constant, this goes away. That, with respect to the derivative of y squared with respect to y, is just 2y. Right? So you're just pretending the other variable is constant while you're differentiating with respect to the original. Right? So suppose now I have this function, x and y, 3x squared, y cubed. If I look at the derivative with respect to x, if this is just a constant, and that's just a constant, then the 3y cubed comes along for the ride, and the x squared becomes 2x. So it becomes 2 times 3, 6x to the 1, y cubed. But with respect to y, this is all now one constant. The 3 comes out, and I get a square there, so it's 9x squared, y squared. Right? Just like we have there. Right, so notice that the partials are not the same by any means. And then my favorite surface from problem number 1 from the last from chapter 4.1, the ripple. if I want the partial of this, so I'm going to just take the derivative of these, not because partial derivatives are that complicated, but this function itself is actually a little tricky to differentiate. So I'm going to rewrite, here are the partials right here. They're similar, except that one has a negative x out in front, the other has a negative y. But let me show you how this comes about. Suppose this is my function, f of xy equals cos. Now instead of putting the square root of x squared plus y squared, I'm going to do x squared plus y squared all raised to the 1/2. Right. So to differentiate that, the first thing I get when you differentiate cosine is you get negative sine, and it's going to be that same thing, x squared plus y squared all to the 1/2. But now I have to take the derivative of what's inside by the chain rule, right? So I have to multiply by, let's see, I bring the 1/2 down, 1/2 x squared plus y squared to the negative 1/2, right? I just brought that out in front and subtracted 1. But now that wasn't just an x either, that was an x squared y squared. So now I have to do the chain rule one more time with respect to x squared plus y squared. When I differentiate that with respect to x, I just get 2x. Right? And these are multiplication signs, not subtractions. Okay, so the 2's cancel, and I get an x here, so I get the negative x sine. This is just the square root of x squared plus y squared, and this x squared plus y squared to the negative 1/2 is just to the positive 1/2 in the denominator, but the 1/2 is just square root. And if you play that same game all over again, only consider y the independent variable, the only change that happens at the very end is when you multiply by the derivative of x squared plus y squared, you get 2y. And so that becomes a y. So there are my partials, the partial with respect to x, partial with respect to y, of a slightly harder function. There's also something consisting of the partial derivatives. It's called the gradient vector, and it's denoted grad f. Right, that is the grad symbol. Right, stands for gradient. It's not delta. Delta looks like that, right? So it's an upside down delta, if you will. So the gradient of a function, of a multivariable function, is just a vector containing all the partials. If it's a function of two variables, x and y, the gradient of that function, just the partial with respect to x, partial with respect to y. Simple examples. If I have f of x, y is x squared plus y squared, there's f sub x, there's f sub y from the previous examples. If I have f of x, y equals 3x squared y cubed, there's f sub x, and here is f sub y. And we got those right back here. And then likewise, for the next problem, keep this in mind. If your function is cosine square root of x squared plus y squared, the gradient of f is just the vector. Remember, the gradient of a multivariable function is a vector with the same number of terms as there are independent variables. In our case, it'll always just be 2. Well, no, in the next example there will be 3. Z will be considered a variable. But look, same thing, f sub x, f sub y. Right? So the gradient produces a vector of partial derivatives. And what this gradient does, there's many applications for the gradient. But one thing it does is that once you find the gradient, it gives the direction in the xy plane that leads to the greatest increase in z for a unit step size. So I'll show you what that means, but let's just consider first our graph here. This is our paraboloid, x squared plus y squared plus 2. Creates that. If I want to find the gradient at the point 2, negative 2, 10, that's this point right there. That's 2, negative 2, 10. Right, it doesn't show up that well. It's that black dot, right? what is the direction to move in the xy plane down here that leads to the greatest increase in my function of x and y here. And you can sort of tell if you were sitting, let's pretend you're on the inside of this little cup and you were sitting right in that dot. If you were to look around you, which way would be the greatest increase? Clearly heading directly up, right? That's the steepest. If you went in towards the origin there, you'd be going down. So the direction of greatest increase looks to be about where that blue arrow is, right? Okay, so let's check. If we do that, so here was our gradient. If you go back to our, let me put it up here, the gradient of our function for this problem is given right here. And I want x is 2 and y is negative 2. So I put 2 into there and negative 2 into there. Right, that's what I mean by the gradient of f at 2, negative 2. And I'm getting it right from my point. Right, x and y. The next one is z. And z is just x squared plus y squared plus 2. It comes from the actual function right here. And when I put those in, it's really simple. 2x, which is just 2 times 2, becomes 4. And 2y, which is 2 times negative 2, becomes negative 4. So if you look at this arrow down here, that is 2 in the x direction and negative 4, because it goes 2 to 4. So there's 4 in the x direction and then negative 4 in the y direction. So that gives you the direction of greatest increase. Right? It means if you go out, if you were standing here and moved in this direction, you'd have the steepest climb to make. Right? And this code over here just shows you how to create this plot. You know, it does that same that's that same surface where you have to find your x and y domain, mesh it out, apply your function, and then plot the surface. And this just gives me the this arrow down here. All right. So that's the gradient. That's what it does. It's a vector of partial derivatives, and it points you in the direction of greatest increase. There's one other very important thing that I can get from the gradient, and that is a normal vector. Specifically, if I have my surface defined like this, all right, remember any function, suppose I had z equals x squared plus y squared plus 2. That's my surface, right? I can just subtract z from both sides, or subtract x squared plus y squared plus 2 from both sides, and I'll do the second one. I'll do z minus x squared minus y squared minus 2 equals 0. So anytime you have a surface defined explicitly, like z is a function of x and y, you can express it in terms of big F of x, y, z equals 0. You just subtract everything on one side from both sides, and one of the sides will turn to 0. Right? So any surface can be expressed like this. And when you get the gradient of that capital F, that gradient of that function, you get big F sub x, big F sub y, big F sub z. And the nice thing about this is that this vector, right, this gradient vector, is normal to the surface, right? So if I have some surface here, then this vector, this gradient vector, is pointing so that it's essentially, right and normal to the entire surface. It's actually normal to the tangent plane, but it's pointing directly out from that surface. And that's what we'll use this for in the next chapter when we start bouncing around in 3 space. And so specifically, if I already have my function defined explicitly, you can always write that, just as I did here, as I take the original function, subtract z from both sides, and I get this form of capital F, x, y, and z equals 0. Or I can subtract little f of x, y from both sides, and I get this form of f, capital F of x, y, z equals 0. Right? And if you take the gradient of either one of these, let's take the gradient of this first one. the partial of this thing, I'll call this left-hand side f of x, y, z. The partial of that with respect to x, well, the z's gone, so it's just the partial of little f with respect to x. So you get little f sub x. And the partial of this with respect to y, well, the z is constant. We pretend it's constant, so it's gone. And I'm just left with the partial of little f with respect to y. And then the derivative, the partial derivative of this function with respect to z, well, these are x and y are constant, so whatever you do to them is constant. So this thing is just gone. The derivative of that with respect to z is negative 1. So I just basically get my partials of the original function and then a negative 1 in the z direction. Had I switched it the other way around, had I used this option over here instead of this option, then my first partial would be negative f sub x, my second partial would be negative f sub y, and then my third partial, the partial with respect to z, would actually have my positive 1. So notice, you get two normals. And that should make sense, because if I have a surface and I have a normal vector here, there's one going in the opposite direction, right? And one's pointing up, because you can tell by the positive z component, and the other is pointing down, right? Okay, so suppose let's do this example here. I have this surface, z equals x squared plus y squared plus 2, our favorite paraboloid. And this is just z equals f of x, y. If I want this normal vector to the surface at the point 2, negative 2, 4, that is pointing down, what I want is this normal, right? Because that's pointing, that negative 1 tells me it's pointing down. Okay, and so it's really quite easy. Now all I have to do, let me clean this up. I'm getting a little messy over here. I don't like all that. Right, so my function, f of x, y, is just x squared plus y squared plus 2. So the partial with respect to x is 2x. Partial with respect to y is 2y, as we've done a couple times now. And then we just use the negative 1 form for the z direction. But now I want this normal vector, which is just a gradient vector, evaluated at this point 2, negative 2, 1. So I have to put in x equal 2 right there, y equals negative 2, and the 10, sorry, that's 2, negative 2, 10. The 10 doesn't get plugged in anywhere because there's no z in this expression. So I just get 4, negative 4, and negative 1. Right? So that's the normal vector pointing in the downward direction. It's this vector right here. So there's that same surface, and this is just what I called n1 up above. It's my normal vector. And what we'll do in the next chapter is we'll say, all right, if I have a vector that is basically perpendicular to the rest of the surface or normal to that surface, then when I come in to bounce off of there, I'll be able to bounce with respect to that normal. That works really well. This is just some MATLAB code over here on the left. You're welcome to grab it from the Chapter 4 program repository and run it. Basically, I'm plotting the point P there. That is the black dot. That's P. And then I have N. That's that normal that I just found over here. All right. And so that this is the vector N. And so I just do the vect arrow that starts, basically that's the arrow function that draws an arrow from this point to this point. So that's just where I'm getting that normal from. And this is the standard sequence of events for plotting a surface. I get an x domain, y domain, mesh it out so x and y are now a full grid and not just single dimensional vectors. Apply my function and then plot it using the surf command. And I hope it looks from this perspective. And what you should do is probably grab this function or this file, run it, and when this graphic opens up, make sure you rotate it around and it should look like this arrow is normal or perpendicular to this surface, pointing directly out from the surface. And that's important. That's an important geometric property, because later when we start bouncing off of things, in 3 space, if I have my normal vector, then whenever I hit this surface with a ball or something, I'm going to need to bounce. How will I know where to bounce? It'll be with respect to this normal. Right? Because if these angles are equivalent, I'll know that these angles are essentially equivalent if you look at just that tiny little it's what's called a tangent plane, right? But I'll know that my incoming angle will be the same as my exiting angle. So it's great stuff, very useful. The normal vector. If you already have the function in this form, capital F of x, y, z equals 0, then you're good to go. You just take your partials, right? And that's something like if you had a plane ax plus by plus cz equals 0, you can get your normal pretty easily. Grad f, well, the partial with respect to x is a, the partial with respect to y is b, and the partial with respect to z is c. That grad f, that's the normal vector. That's how we started creating planes in the first place, as we said, if we have a normal vector, then our plane looks like this. Sorry, there's a constant maybe at the end. Right? So it works out great. We use our normal to create a plane, and then if you look at the plane and get its gradient, you actually get that normal back. And then we can bounce around in 3 space using these normals to help us guide our bounces. But that's chapter 4.3. We are wrapped up for chapter 4.2, and I will see you later. Bye.